So hello everyone, welcome back to this week's algebraic graph theory seminar. This week, Dheer is going to talk about the spectral Turán problems for trees and even cycles.
Thank you to the organizers for the invitation to speak. Happy July 4th to anyone celebrating. So today I'll be speaking about spectral Turán problems, and specifically towards the end we'll be looking at some of the methods we've developed applied on some bipartite graphs, for example, even cycles and trees. Right? But before we get into spectral Turán problems, I'll describe what the Turán problems are. So one of the central functions in extremal graph theory is the Turán number, which is the number for any particular graph F, where you fix the number of vertices n, and you're trying to maximize the number of edges in any F3 graph on n vertices. Okay? And the notation we'll be using for the Turán numbers is this: small ex and f. And related to it is the extremal configuration of graphs which have these many edges and don't see f as a subgraph. And we'll be using capital Ex, n for the number of vertices, and f for the forbidden subgraph. Right. And so this field started long ago. Mantel's theorem is one of the first results, if not the first, where you're forbidding the triangles and trying to figure out what is the maximum number of edges. And n squared by 4 turns out to be the Turán number for triangles. This is further generalized to forbidding any complete graph by Turán's theorem. And one sees that the extremal configuration is the complete multipartite graph where each part is of almost equal size. And the number of edges in such a graph is approximately 1 minus 1 over r, where this r is related to the size of the forbidden complete graph times n squared by 2. Right. And then this is generalized to any graph of chromatic number r plus 1 by the Erdős theorem. And it turns out that if r is at least 2, so if we're looking at least chromatic numbers, if you're looking at forbidden graphs with chromatic number at least 3 or more, then we have the exact asymptotics of the Turán numbers. So this formula gives us the exact asymptotics. We know that there's order of magnitude is n squared, and we also have the constant term which comes along with it, which is about 1 minus 1 over r plus or minus some small o of 1 error term, small o n squared when it gets multiplied to this. All right, and so Erdős is very good. It gives us a nice result for when our forbidden graph has at least 3 colors. Now, if your forbidden graph is bipartite, then all it really tells you is that the Turán number is small o of n squared. So we don't have much in those cases. But so the bipartite case is a beast of a problem of its own. And there are results for some basic kinds of bipartite graphs, but a lot is unknown. So for example, the Kováry-Sós-Turán theorem gives an upper bound for the Turán number for complete bipartite graphs. And one can see that this is of the order of n raised to 2 minus some epsilon. And matching lower bounds have been found for only a small set of complete graphs. For example, when both S and T are 3, or when T is much, much bigger than S. Right. Some other basic bipartite graphs would be the even cycles. So when we're forbidding the even cycle, there are some results which have been known for a long time for upper bounds for the Turán number, but matching lower bounds haven't been found for many cases. So we have matching lower bound, matching order of magnitudes for only 3 cases so far, C4, C6, and C10. So C8 would be the next thing to go for. If you could show that the order of magnitude when forbidding C8 is of the form of n raised to 1 plus 1 by 4, then that would be great. Right. And for trees, the Erdős source conjecture says that if your average degree is at least k is more than k minus 2, then you're going to contain all trees on k vertices. So for the path, this is known to be true, but for other trees, we still don't know. So for example, consider you're forbidding trees on 5 vertices, k minus 2 is 3. So we're saying that any tree with average degree more than 3 is going to contain all trees on 5 vertices. And the extremal configurations in these cases come from just taking disjoint copies of some cliques on one less vertex. So this is still open. We have an upper bound for the Turán number of any tree, which would be 2 times. So if we allow for our average degree to be twice what we want to show it to be, so if we allow for average degrees to be up to 2 times k minus 2, then we have a trivial upper bound for the Turán number, but we want to bring it down to k minus 2. Also, please feel free to ask any questions that you may have in the middle of the talk. All right, so I mentioned we'll be talking about spectral Turán numbers because that's what the title says we will do. So why do we do spectral graph theory? So we do this because when we associate graphs to matrices, especially if there's a symmetric matrices like the adjacency matrix, which we'll be looking at, then this opens up a variety of linear algebra results, which we can apply to our graphs and figure out properties of our graphs from that. So in particular, for the adjacency matrices, we have a complete basis of real eigenvectors, and associated to them are real eigenvalues. So we can order them from increasing to decreasing, lambda 1 to lambda n, if n is the number of vertices. And we will, because it's important to us for this talk, we'll be calling the largest eigenvalue as the spectral radius. And the spectrum which we get from a graph's adjacency matrices really tells us a lot of information about the underlying graph. For example, you can figure out what the number of edges are, what the number of triangles are, or any number of closed walks in a graph by just looking at the sums of the powers of the eigenvalues. And also we have, with respect to each row in our matrix, we have eigenvalue eigenvector equation, and we can use these to study a lot of properties of the graph. Right, so I just want to describe the spectral Turán problem in this slide. But a more general problem is what is called the Brouwer-Solhate problem, in which you're forbidding, in which you're looking at a set of graphs which are F-free, and you're, sorry, not necessarily F-free. In the Brouwer-Solhate problem, we just look at a set of graphs and we try to figure out, we want to maximize the spectral radius. Nikiforov's description of spectral Turán problems is just an analogous to Turán problems, where now the set of graphs which we look at are all the F-free graphs on n vertices, and we want to, instead of maximizing the number of edges, we want to maximize the spectral radius. So spectral Turán problem is basically the same constraints as the Turán problem, but our objective function is to maximize the spectral radius instead of the number of edges. And our notation will be similar. We just use small specs and capital specs for the maximum value of the spectral radius and the set of extremal graphs. And the reason we want to set this new problem up is not only to maybe create some easier problems, but also because these might in turn go back and help us solving the Turán problem. And the reason that there is such a chance is because your spectral radius gives us a upper bound for the average degree. And so if you're maximizing your spectral radius, if you're getting an upper bound for your spectral radius, then you're also getting an upper bound for your average degree, which multiplied by this n/2 term just gives you an upper bound for the number of edges. So chances are that we can get some Turán result by looking at spectral Turán problems. Okay? And so Nikiforov answered the spectral Turán question for the complete graph, and he showed that the spectral radius is maximized by the same Turán graphs, which were maximizing the number of edges. And so this result, when combined with the average degree spectral radius relation, also implies the Turán theorem. It tells us that the number of edges when forbidding a complete graph is achieved by the Turán construction. So this is just a strengthening of Turán's result. Not only does it maximize the number of edges, but it also maximizes the spectral radius. And so our hope is maybe to find other graphs whose extremal numbers, whose Turán numbers we don't know, and then by just studying the spectral problem, we can achieve something for the Turán problem. Right, so now just a comparison for some of the results for a variety of forbidden graphs. So we're just going to be looking at what the Turán graphs look like and what the spectral Turán graphs look like. When we're forbidding complete graphs, they're going to be the Turán graphs, as we saw. If we forbid odd cycles, it's again the Turán graph on two parts, or you can say it's the complete bipartite graph with balanced parts. And so on the left, actually, so Furedi and Gunderson proved this for some values of n, large enough values of n with respect to k, but other parts have been proved by other people. I just didn't put a big list over here. All right, so we might feel that maybe the two problems are the same till now because their extremal families have been the same. But as an example, when we're forbidding C4, the spectral radius is maximized by the friendship graphs, which are k triangles intersecting at one unique point. But the Turán result comes from some kind of algebraically defined graphs, graphs coming from projective planes, specifically the polarity graphs of projective planes, when the number of vertices is good. So these graphs look really regular, while our friendship graphs are extremely irregular in some sense. Okay. So let's move on and look at some other forbidden graphs. So for this, let's define friendship graphs and fan graphs. Friendship graphs are what we just saw, intersecting triangles at a unique point. These can be generalized to define what we call fan graphs, which are take k copies of some clique kr and intersect all of them at one unique point. Example is on the left, where we're looking at 3 copies of a k4 intersecting at the unique vertex, which is colored red. So I mentioned that the Erdős theorem gives us the asymptotics of the Turán numbers, but it is still interesting to figure out the exact values of the Turán numbers. So since the friendship graphs are 3 chromatic, we know that the order of magnitude is going to be n squared, and we know that the constant term which comes with it is 1 over 4, but it is still interesting to figure out what the exact number is, and which basically means figuring out what that error term, how you can reduce the error term, which you had in the Erdős formula. And so Erdős, Furedi, Gould, and Gunderson did this for the friendship graphs, and they found that if you're forbidding the friendship graph with, say, k copies of triangles, then you can take k minus, you can take a complete balanced bipartite graph and input some regular graphs into one part, and you can, you can embed some regular graphs into one part, and you should get the extremal construction. And so what Choba, Feng, Tate, and Zhang did is they showed that the spectral extremal graphs also have maximum number of edges. So there's some things I'm skipping over, which is sort of like over here, you might have some more graphs where by taking these graphs to be slightly imbalanced, you might get some more edge extremal graphs. But the spectral extremal graphs are attracted to the parts being equal. So that's why there's a containment. Right? And the friendship graph result was generalized for fan graphs, and it was shown that the Turán number is what appears over here, and it is achieved by looking at a Turán graph on one less part and inputting two regular graphs of not too big a size into one of the parts. So over here, I'm just inputting cliques because they're the easiest to visualize, but you can put in some other regular graphs with the same regularity as the clique I put in. And we managed to generalize this for, we managed to generalize the association between the two families for the friendship graphs to that for fan graphs. And we showed that the spectral extremal graphs are also edge extremal. That is, they have maximum number of edges. All right. Next, we'll look at some odd wheels or wheel graphs. A wheel is a graph on T vertices, which is formed by joining a cycle on one less vertex to another, or to a new vertex. So you take a cycle on T minus 1 vertices and join each of the vertices in it to a new vertex. We call a wheel odd if the total number of vertices is odd, and we call a wheel even if the total number of vertices is even. Even wheels are 4 chromatic and odd wheels are 3 chromatic. I'll talk about this later on, why this is important. Right. So now we'll be focusing on the odd wheels. The Turán numbers for when the wheel has 5 vertices and when the wheel has more vertices are slightly different. So the constructions are slightly different from each other. For the wheel on 5 vertices, the extremal number looks something like n squared by 4 plus n by 2. And you can see that the n squared by 4 is coming from this balanced complete bipartite graph, which is underlying it. And the n by 2 comes from embedding maximal matching inside each of the parts. And so what we were able to show was, again, the spectral extremal graph, which you get, has maximum number of edges in the W5 case. And for larger odd wheels, the structure is slightly lopsided. What the Turán number is doing, it's maximizing this particular thing where n naught is the size of one part and n minus n naught is the size of the other part. So n naught times n minus n naught is the number of edges in this underlying complete bipartite graph. which has parts of maybe possibly slightly different sizes, and by embedding a regular graph of size of degree k-1 into one of the parts and doing calculus, we can figure out what the extremal structure is going to be. So in particular, so what the extremal graphs looks like are, you have a complete bipartite graph. You have one edge in the smaller part, and in the larger part, you're embedding a k-1 regular graph where the components aren't too big, because if you have a large part, then you would end up embedding a wheel. So we want to avoid that. And what we ended up showing is, in this case, the spectral and edge Turán graphs are completely disjoint. If your k is large enough, in particular, if your k is 6 or more, the spectral Turán graph is attracted to having balanced parts, while the edge result is going to incentivize having a larger part for the portion which has a regular graph embedded into it. Okay. So when k is equal to 3, again, we would have equality because the parts end up having equal sizes or almost equal sizes, I think. But for k equals to 4 and 5, the question is still open, and that is because one of our lemmas didn't go through. So we're not sure whether to put a k4 into one of the parts and just one edge in the other, or should we put in triangles into one part and a maximal matching inside the other part. And similarly for W11, it's putting in a 4 regular graph into one part and one edge into the other part, versus should we put in a 3 regular graph into one part and a perfect matching in the other part. So yeah, the lemma which we were using is sort of on the degrees, on the sum of the degrees inside each part. So we can see that 3 plus 0 is equal to 2 plus 1. And so, yeah, we're not sure as to which configuration would maximize the spectral radius, because they're pretty close to each other. Right. And I mentioned the chromatic number is interesting previously. And this is because if your forbidden graph is color critical, which means if there is some edge inside it, deleting which you reduce your chromatic number by 1, then it was shown by Nikiforov that such a graph would have a spectral extremal graph, which is also edge extremal. And the even wheels are an example of color critical graphs, where your chromatic number is 4, but deleting any edge reduces your chromatic number to 3. So all even wheels were taken care of, and both extremal graphs end up being Turán graphs for color critical graphs. There are similar results for hypergraphs as well. So yeah, and it would be interesting to see if the other methods which I will mention soon can be used for hypergraphs as well. Right. So we've seen a bunch of results where the spectral extremal graphs are edge extremal, and then there's some cases where this doesn't happen. Conjecture of Mike Tate is that if your extremal graphs, if your Turán graphs, if your edge extremal graphs look like Turán graphs plus some constant number of edges, then the spectral extremal graph is also going to be edge extremal. And there was a paper in March on the arXiv, which hasn't been published yet, which says this is indeed true. But I haven't checked that. But that's pretty interesting. It would be interesting to see what would happen if we increase this error term. What happens if it becomes linear or something? All right. So now I'm going to go on to the bipartite problems, that I said I would talk about. So before we get into that, I'm just going to describe these two graphs. SNK is the graph obtained by taking the join of a clique on k vertices with an independent set on n minus k vertices. And SNK plus is the graph obtained from SNK by just adding an edge inside the independent set. Okay. And a conjecture of Nikiforov was that if your spectral radius is at least as much as the spectral radius of SNK, then it must contain either the odd wheel on 2k plus 1 vertices or the odd cycle on 2k plus 1 vertices or the even cycle on 2k plus 2 vertices, unless G is the graph SNK itself. So this can be thought of as saying that specs of n comma c to k plus 1 comma c to k plus 2 is equal to SNK. So the spectral extremal graph when forbidding c to k plus 1, c to k plus 2 is SNK. And similarly, the other part of this conjecture is that if your spectral radius is at least as much as the spectral radius of SNK plus, then you should contain the even cycle c to k plus 2. So I mentioned that the Turán numbers for even cycles is still open. The next thing to study would be C8 because we don't have a matching lower bound for that. But this conjecture aims to answering the spectral Turán version of that even cycle problem. And there's a similar conjecture for trees for the Erdős source problem, which goes if your spectral radius is at least as much as SNK, then you're going to contain all trees on 2k plus 2 vertices, unless you are the graph SNK. And similarly, if your spectral radius is at least as much as SNK plus, then you're going to contain all trees on 2k plus 3 vertices, unless you're the graph SNK plus. This can be interpreted as saying that maximum of specs, where now this is small specs, so it's the spectral radius, the value of the spectral radius for any tree T such that the cardinality of V of T is equal to 2k plus 2 is achieved only by SNK. And similarly, for 2k plus 3 is achieved only by SNK plus. So we started off trying to analyze the C8 case, and we ended up showing that the spectral extremal graph for this is SN3 plus. So this is the even cycle problem again. We'll come to the Erdős source problem later on. So for the C8 case, we showed that this conjecture is true. And then it turned out that we can just generalize our proof and use it to show that for all even cycles, C to K plus 2, the spectral extremal graphs are going to be the SNK plus. And this could be further generalized for the first part of that conjecture where you're forbidding a pair of consecutive cycles. All right, and then we thought of whether or not we could use the same techniques to answer the Erdős source, the spectral Erdős source problem. And it turned out by just making a few tweaks, we were able to. And so maybe I'll describe the following methodology that we used by using the Erdős source problem as an example. So the basic method is, so we're trying to show that some graph is spectral extremal while forbidding some subgraph F. Now, we have some spectral extremal in mind, maybe. So the spectral radius of this guess graph, which we think is spectral extremal, let's call it G, is going to give us a lower bound for the specs. Now, once you have that your spectral radius is going to be at least this big, that would constrain what your graphs can look like. If your spectral radius is maybe too big, then maybe you have a lot of edges, depending on what the forbidden graph was. Once you have a rough structure of what the extremal graph should look like, you can get information about for the leading eigenvector, for the Perron eigenvector. Once you get information on the Perron vector, then you can go back and improve your estimations for the structure of the graph. And then that in turn would again give you more precise information for the Perron vector. And you can just keep going between the two, between the third bullet point and the fourth bullet point, until you're close enough to your guess graph that you can show that just altering to your guess graph is just going to help you. So for example, for the spectral Erdős source problem, what we ended up showing by doing this cycle between the structure of the graph and the Perron vector was that we ended up getting that there is a complete bipartite graph with one of the parts of size k embedded inside our graph. And then it turns out that the set on n minus k can have only one more edge in there, else you'd end up having a tree on 2k plus 3 vertices. And that's a problem. So just add that thing over there, add that edge over there, and put all the edges inside the part on k sizes, and that doesn't create a tree. So we end up showing that SNK plus is the extremal graph for the 2k plus 3 tree problem. And the 2k plus 2 is just similar. You don't attach that edge inside the part on n minus k vertices. So we're just going through some of the details of the proof. So we know that the spectral radius of SNK is going to give us a lower bound for the spectral radius of our guess graph G, which for now is SNK or SNK plus, depending on which problem we're looking at. And the eigenvalue for SNK, the spectral radius for SNK can just come by looking at a quadratic polynomial, which we get from the quotient matrix of SNK on two parts. And one can see that the lower bound for this is root kn. And I mentioned how we get a lot of eigenvalue eigenvector equations by just looking at the adjacency matrix times the Perron vector. We can also look at powers of the adjacency matrix. So we can look at a square x equals the Perron vector, and a square x equals lambda square x. We can just look at this equation, and at the same time, we know that the eigenvalue is going to be bounded above by the maximum degree. So the maximum degree of a square, and the maximum degree of a vertex would basically just be a row sum, the maximum row sum of the matrix. So lambda square would be bounded above by the row sums in the A square matrix. And so we can do this and we end up getting this upper bound as well, which is, you can think of it as root 5kn for simplicity. Yeah. All right. So we have some lower and upper bounds for lambda 1. We then partition the set of vertices into two parts, those having large weights, call them L for large, and small weights, which we use S to describe, denote. All right. And so if we have a lot of vertices with large weights, we'd need a lot of neighbors having large weights. Um, in particular, what we'll be looking at is the A square matrix. So we'll have a lot of vertices in its second neighborhood, um, which have large weights, but that would end up forcing us to have a lot of edges between the neighborhood of a vertex with large weight and the second neighborhood. And this would force trees inside. So the idea is basically that um, you can't have too many edges between the first neighborhood and the second neighborhood of any vertex, because otherwise you end up having a tree. And so yeah, this ends up giving us that there are small O of n many vertices of large weight. And then we show that you need to have a large neighborhood for any vertex in L. That is, it should have order n. Um, else you'll end up needing a lot of edges again inside this bipartite graph. Okay, and then a simple upper bound for the number of Turán number for any tree, which is 4k, which is 2k plus 1 by 2, is going to tell us that there can be at most constant many vertices in L. So the summation of the degrees is at most 4k plus 2 times n, because we know that the Turán number for a tree is 2k plus 1 times n. And so there can't be many vertices which have degree n, else we would cross this number. So that tells us that there's at most a constant number of vertices in L, and then we just refine our arguments. We end up showing that every vertex inside L has almost constant eigenvector entry. And you can show something like, say, we scale our vector so that the maximum entry of the Perron vector is 1. And say we take a vertex in L which has weight C, then V is equal to C, then the degree of V is going to be at least Cn minus epsilon n. So we can show that every vertex in L has almost degree C times n. And again, to show this, we're going to rely on showing that if that isn't the case, then there's going to be too many edges in the bipartite graph between the first neighborhood and the second neighborhood of some vertex. And the next step is showing that any entry is going to be close to 1. And that also sort of follows the same logic. So we end up showing that all the vertices in L have degree close to n, and that forces us to have at most exactly k vertices inside L. So now we know that we have some subset on k vertices over here, which has a huge common neighborhood. And now it comes down to showing that this common neighborhood has size n minus k, just basically saying that there can't be some vertices which are adjacent to only a portion of L, but not to the others. And so that's showing that there are no atypical vertices in S, which requires some work. But once we do that, we can say that the complete bipartite graph of paths k and n minus k is contained in G, and then just altering to S and k plus is only going to increase our spectral radius. And that completes the proof. For future work, where the spectral extremal problem is still open for these on 9 and 11 vertices, and what we showed was that the maximum of the spectral Turán numbers for trees on 2k plus 2 and 2k plus 3 vertices is achieved by snk and snk plus, but we still haven't answered the question for what is the spectral extremal for a fixed tree. For the Erdős source conjecture, it involves showing that the path, the extremal graph for the path is going to be the extremal graph for everything else. But for us, we end up having different extremal graphs, because one can see that SNK and SNK plus have a lot of trees embedded inside them of sizes 2k plus 2 or 2k plus 3. So that's an open question someone can look into, and also applying this for our methods for other bipartite graphs and maybe even hypergraphs. That's all. Thank you.